Hi, people that watch educational videos for fun. My name is Sohum, and I'm a senior in the Joseph Wharton Scholars Program, studying finance and electrical engineering. I'm also part of the Jerome Fisher Program in management and technology. Together, Joe and Jerome form JJ, who is not to be confused with the other JJ in my life, Jimmy Jones. They've given me many opportunities to research and explore my curiosities at Penn. For this Ben Talk, I'd like to share with you the findings of my senior design project, which has been done under the supervision of Professor Liang Feng in the Material Science Engineering Department, and also with my co-engineers, Ben Grau and Justin Chang. This Ben Talk is about a story, about the next revolution in computation. It's a revolution in optics. It might get a little bit scientific, but I'll try to keep it a bit entertaining and fun. So here's the story. In our lifetime, we've seen computers shrink from the size of a classroom desk to something that can fit on our wrists. Our parents' generation have witnessed something even bigger. They've seen vacuum tubes that have been the size of buildings operated by teams of engineers to a sleek and yet still ugly pocket-sized TI-84 calculator. It was once a pipe dream to think that normal people could own machines capable of solving their math homework in a matter of milliseconds. Just imagine what a college students of the 70s would say if you told them that one day they'd be able to find a date, order a pizza, watch Happy Days, and listen to Pink Floyd all at the same time on a device in the palm of their hands. What they do is they pass you the joint and say, "Far out, dude," or whatever it is that people from the 70s used to say. We've come quite a long way from the early days of the computer, but we're dreamers, we're not historians. We wonder about our kids and future generations, of students, of professionals, entertainers, and everything in between. And unfortunately for us, the limits of technological improvement on state-of-the-art computer chip technology are being realized due to the limits in the transistor-based manufacturing. Now, I know this is some technical jargon, and I'll break it down. So what exactly does it mean that we're reaching these limits? It means that the next generation will find it difficult to unlock the future of their technological potential because the size of the computer chip itself cannot be scaled down further. In the graph presented, the green line is the rate at which we should be improving computer speeds. However, the blue line, either shade, pick any, is what's actually happening. We're plateauing, and that's not good. My team and I are solving this issue. We've developed a chip that uses light and lenses to make computations faster and on a substantially smaller scale, giving people the same thrill of leaps in technology that we had experienced, that our parents had experienced when we were growing up. So let me tell you a little bit about how this works. It all begins with the lens. It's hard to tell, but right now I'm wearing contact lenses. And they're curved in a way to take in an object in the distance, like a stoplight, and bring them closer to me by focusing the object. It's great for me because I can see sharper images, and it's great for you because if I can see the stoplight when I'm driving, I'm less likely to T-bone you. So what's going on is that the lens is slowing down some light waves while not changing other light waves, causing light to bend and meet at a focal point, as shown below. Depending on how blind I am, which on the scale of Iceman from Top Gun to Stevie Wonder is at a solid -6, the focal point can be shifted to restore my vision. Now, at the focal point, some weird things start to happen. Specifically, the lens produces the Fourier transform of light. That's a concept so confusing that Penn has an entire course for it, which has a difficulty of 3.7 out of 4. And that's the magna cum laude of course difficulty if you're into Latin honors. Here's a 1.0 difficulty out of 4 explanation. The Fourier transform takes an ordinary object, like a song or a painting, as you normally see it, and puts it in a new form. Imagine taking the Mona Lisa, and instead of seeing a debatable masterpiece on a canvas, you're left with a bucket for every color used in the painting. And the bucket is filled with as much color as was used in the painting. So if a painting, let's say the red square in a white background, the modern art painting, was used in our Fourier transform example, there are 2 colors, red and white. There'd be 2 buckets, one filled with red and one filled with white, in an amount corresponding to how much was actually used in the real painting. So I hope that makes sense. If it doesn't, you can take Math 241 and probably say goodbye to your hopes of graduating magna cum laude. With this Fourier transform, the buckets of paint from old Mona, we can easily change the original image. For example, we could delete or empty the bucket filled with brown paint in the Mona Lisa example. Then, when we resurrect Leo, and that explanation is for a separate Ben talk entirely, and ask him to repaint Mona, we'd be left with a bald lady that probably would barely make it to the basement of the Louvre. With computers, we can do this process really quickly and with lots of sophistication. Take the Bohemian Rhapsody and apply the Fourier transform, delete the really high-pitched notes, reapply the Fourier transform, and we're left with 2 instead of 3 Galileos. But that's a silly example. Rather than doing silly stuff, we can do math, which is quite serious. We can take light signals bearing information, transform them, slice, dice, add, subtract, multiply, divide, put them all back together as a light signal. With billions of these individual operations, just simple mathematical operations, we've made the computer, which is just a bunch of tiny mathematical operations used to create a big mathematical operation used to buffer your canvas space that shows just how badly you did in Math 241. Now, obviously, we can't make computer chips with lenses. The Electrical Engineering Union clearly bans any optometrist from seeing computers as patients. Also, lenses are too big to fit in your Apple Watch. What we did is build a device that acts like a lens. It bends light with little bits of gold that are shaped like the letter V, each with a precise orientation and size. Each V, technically called a scatterer because it scatters light, is on the order of nanometers. For reference, here's a good analogy. Imagine taking a meter stick, multiplying it by 10 to the negative 9th power. You now have a nanometer stick. That's a nanometer. With the scatters, we can produce the focal point, and we can do math, which is the best ending for any story. So that's the explanation for how it works. And if you follow that, you're either lying or you're crazy. If it's the latter, you should probably quit your day job as a serial video watcher and become an electrical engineer. The last thing to consider is where this can be used. In various technological domains, from big data to artificial intelligence, the demand for computation and the need for scale and computation has increased quickly. Our system provides a complement to purely electronic architectures by increasing the speed of data processing while decreasing the size of devices and power consumed. What does this mean for you? Well, it means that you could play PlayStation 4 quality games on your Apple Watch without having to recharge 5 times a day and take a second mortgage on the house. What does that mean for me? It means that my Canvas page shows my Math 241 grade loading way faster. It's like ripping off a bandage. Ultimately, breaking the barriers in size, speed, and power provides the fundamental changes for computing technologies. And to that end, I want to mention that the process of building our device has been extremely rewarding. I'm sure that someone will ask me about Fourier optics and computation during my finance job after graduation. Thanks for listening.